Let's learn some circuits. All right, first question. You want to know how to hook up an ammeter and a voltmeter to measure the total circuit current and the voltage across the battery. It's going to be this guy because the voltmeter has to be connected in parallel across our total voltage, which it is right here. It's not right in any of the others. And the ammeter must be in series in such a way that all electrons must pass through it if you're looking for a total circuit current. And so that's the one there. Next guy. For this one, we want to find the current through the 10 ohm resistor. Now, you'll notice if an electron's leaving here, there is no way around the 10 ohm resistor. So really, current through the 10 ohm resistor is just our total circuit current. So we can find that if we've already got the total circuit voltage, we just need the total circuit resistance. Now, I've already started this question because my bloody program crashed on me. But that's okay. This is a parallel resistance formula just to find the equivalent resistance of this section. Turns out this has a net resistance of 22.2 ohms. So our total resistance would be the resistance of the parallel section plus the resistance of this series guy here. So our total is just equal to 32.2, leading to our total current equaling the total voltage divided by the total resistance, just using Ohm's law. So that's just 12 divided by 32.2, which is equal to 0.37, like 3 or whatever, or 0.37 amps. Next guy. Now, this is a little bit funny and might trip you up. We're saying in an electric circuit, we've got this many electrons, and this is a very specific amount of electrons, flow past 1 point in 10 seconds, or 0.1 seconds. What's the current? This is definition of 1 coulomb of charge. That's that many electrons makes, or negative 1 coulombs is that many electrons. So an amp is a coulomb per second, so all we got to do is do 1 divided by 0.1, because amps, or let's do current. Current is equal to charge divided by time, which in this case is equal to 1 coulomb or negative 1 coulomb, whatever, divided by 0.1 seconds, and that equals 10 amps. Now, how you'd recognize this as 1 coulomb is in your data sheet, you have what's called the elementary charge. Which is like 1.6 times 10 to the negative 19, kind of like coulombs per electron or whatever, or proton. Negative if it's electron. So if you got coulombs per electron, if you want to know electrons per coulomb, you just do 1 divided by this guy, or this to the negative 1. So 1.6 times 10 to the negative 19, 1 divided by that equals 6.25 E18 coulomb, or sorry, electrons per coulomb. And it's frozen on me again. Hopefully this is still working. We will see. Oh, is it working? So it's electrons per coulomb. All right, so that's it. That's how you do that question. Current is a measure of the charge passing a point in the circuit in a given time, coulombs per second. That's just how it's defined. We got a 12-volt battery, transfers 33 coulombs of charge to an external circuit in 7.5 seconds, and we want to know the current. So all we got to do is 33 divided by 7.5, because this is just I is the charge passing a point per time. So 30 divided by 7.5 would be 4, so I think this is 4.4. If I'm wrong, just go with whatever this actually equals. We want to find the resistance of the circuit, so that would just be resistance is just V divided by I, which would in this case equal 12 from here, divided by the current we found, 4.4, which is 2.7. Ohms. And we want to find the power output of the battery. I usually like using the formula voltage times current because it's got the least terms in it. So just 12 times 4.4. So if we do 12 times 4.4, we've got, I should be able to do this, 52.8, I think. Yeah. 52.8 watts. Power is measured in watts. And this circuit is likely to be, based on these options, a bulb. So probably an older school like bulb, because these questions are old. These days it would probably be more like 7 watts at the same amount of light, which is kind of cool. All right, assume the battery has a resistor in series before the light's in parallel. 2 identical light bulbs wired in parallel to a battery are equally bright. When one of the bulbs burns out, however, the other bulb is observed to glow brighter. Using principles of physics, explain why the battery causes the remaining bulb to glow more brightly. So here's kind of your situation. You've got a some circuit with some resistance, and then it's going and it's splitting between these 2 bulbs, which are basically resistors. Though honestly their resistance changes with the temperature, but we won't go into that. So if one of them burns out, you're actually breaking the circuit, so there's no current flowing there. So before we had a certain amount of current going through this. This was kind of like a very small part of the total resistance, or it would be a lesser part because, you know, it would just have half the resistance. And so it would have half the voltage drop. Well, maybe not quite half. Anyway, it would have less of a voltage drop if it's a less percent resistance of the whole circuit. Because if you got 50, like say this is 70% of the total resistance of the circuit, it'll have 70% of the total voltage as the drop across it. That's kind of a trick. So anyway, like back when both of these were working, the resistance of this section of the circuit was lower. But if one of them burns out, then suddenly it's not in parallel anymore. The resistance of this section has just doubled. And so as a percent of the resistance of the whole circuit, this has gone up significantly. And so the voltage drop across it has gone up. So we've got a bigger voltage drop across this guy, which will shove more current through it and make it glow brighter. So that's why. Bit of a tricky one, but that is the gist. Next guy. So this involves terminal voltage. Terminal voltage is just, well, you basically pretend every battery is secretly like this perfect battery, but some moron went and put a resistor in there in the package with it. Now, there's no actual resistor in there. It's just pretend, really, just as you make a battery. It's got some effective resistance. You can't make a perfect battery without some resistance to it. But what ends up happening is the more current that flows, the lower voltage you would measure at the battery because you're losing more and more of the energy inside the and voltage inside the battery itself if current is more. So all we got to do is figure out what the drop is here and take our theoretical max voltage and subtract how much we'd lose across here. So our drop right here, so our drop across the internal resistance is 2 times 0.5. So we're dropping 1 volt across this internal resistance. So it's going to be 1 volt less than our theoretical max. 1 volt less than 6 is 5 volts. So if you want to use the formula, it's, what is it, V terminal equals the theoretical max minus I times R. So in this case, it was 6 minus 2 times 0.5. You just want to formula it. Then we got this guy. This one's killer. One of the hardest ones in the package. So we want to know the total power dissipated by the 3 resistors. Now we could solve for this guy, but we don't actually need to. We've already got the total voltage. If we can find the total current, we could just do that, because the 3 resistors are the whole circuit. They're the only things dissipating power. So if we get total voltage and total current, that'll give us our answer. Now, total current will be a little tricky, but if we could possibly find the current through the 10 ohm, then we'd be in business. And to find the current in the 10 ohm, we'd need to find the voltage drop across the 10 ohm, which is not 24. But we know gains equal drops. And so current across, or voltage drop across the 10 ohm plus voltage drop across this parallel section have to add up to 24. And I bet we can find the voltage drop across this parallel section because we got a bunch of information about this resistor. We know it's 9.2 watts. So that's going to be our approach. We're going to say, hey, I'm going to find the voltage drop across here because I know power equals V squared over R. So V is just equal to the square root of P times R. So that will just equal the square root of 9.2 times 33. So if I do that, I get 17.4. So I know I'm losing 17.4 volts across this resistor, but since it's in parallel with that guy, it's the same voltage drop. So gains equal drops. So I gained 24 across the battery. I've lost 17.4 across this parallel resistance section. And so my drop across the 10 ohm has got to be the remainder. So that seems like our V drop across the 10 ohm is just equal to 6.6. Now, if I know that, and I know it's 10 ohms there, I can find the current through the 10 ohm, which is just equal to my total current. That would be the voltage drop across it, which is 6.6, divided by its resistance, which is 10. So I know it's 0.66 amps is my total current. And I know my total voltage is 24. So my total power is equal to my total voltage times my total current. And so that's just 24 times 0.66, which is basically like 2/3. 2/3 of 24 is just 16 watts. And that's how that sucker is done. Easy. A mere 1, 2, 3, 4 steps. Not a problem. Next guy. We got this lovely fellow. We want to know the EMF of the battery, which is this theoretical max voltage. So all I'm going to do is I'm just going to pretend this is a resistor like any other, and just like I'm solving for the voltage of the battery, because that'll be the easiest approach. Much like before, we've got info about one of the branches of our parallel section, so I'm going to use that to find the voltage drop across the one resistor, which happens to be the voltage drop across all of them. So I'm going to be like, okay, my V drop across the parallel section is just equal to the current through this resistor times the resistance of that resistor. Is drop across one is drop across them all. So I'll do 0.14 times 50 V equals I times R. And that just gives me 7 volts. So I got 7 volts across there. Now, if I got 7 volts across there, I can figure out my total current if I find the resistance of this whole thing. So the resistance of the whole thing, I can use this formula, 1 over RT equals 1 over 33 plus 1 over 50 plus 1 over 68. So I'll go throw that in my calculator. Now I got 15.4. So it's 15.4 ohms. Now that I got the resistance there, I can find the total resistance for my circuit. So my R total. I could also find total current at this point. My I total is equal to the current through the whole parallel section, which is just equal to 7 volts divided by 15.4. So if I do that, get like 0.4 something. 0.45. So I found my total current. Now I just need to find my total resistance. This might be better called para. That's the parallel resistance. My parallel resistance is 15.4. So my R total is just going to equal 0.8 plus this 15.4 for the parallel section plus 10. So all that together would be 26.2 ohms. So I got my total resistance, I got my total current. So if I just put them together, I'll get my total voltage, which in this case is the EMF. The EMF. So we do 0.45. We're just doing Ohm's law, so I times R. 0.45 is my total current, and my total resistance is 26.2, and I get 11.9 volts. Now we want to determine the power dissipated in the battery's internal resistance. That's not too hard to do. We've got the total current, which passes through the internal resistance. So that's the current through the internal resistance. And we know this awesome formula, which is power is I squared R. So we'll just use our total current, which is the current through the internal resistance, because there's no way around it. 0.45 squared. And we'll multiply that by the resistance of the internal resistance, which is 0.8. So 0.45 squared times 0.8, and we got 0.162 watts. All right. Next guy, we got which of the following combinations of 3 identical resistors has the least equivalent resistance? Now, I think of these like roads. You could totally solve for this if you just say they're all, each of them is 2 ohms or 1 ohm or whatever makes the most sense to you. But honestly, I like thinking of these as roads. Like, what is the best road setup? Would you rather have like 3 long roads you got to go through one after the other? Would you rather have a point where you can pick one short road or two roads stuck together into one longer road? Would you rather have to pass through one road and then have a choice of one or two? Or would you rather be at this point, point A, and wanting to get to point B, and you've got the choice of 3 short paths? This would be my preference. That's going to be easiest. So that's kind of like a logical way to work through it. Let's say I wanted to make each resistor with the value of 6 or something. Like if I made them each 6, then we'd have 6. This would have a total resistance of 18. This would have a path of 12 and a path of 6. And then if you do your like thing there, you'd have 12 times 6 over 12 plus 6. So what was 72 divided by 18, which is equal to 4. So better for sure. Here you'd have 6 divided by 3. This would be 2 ohms. And for this one, you'd have 6 plus 3. So this would be 9 ohms equivalent if they're each 6. So you can do it this way too if you wanted to more mathematically do it. But you can seriously just be like, hey, which situation would I rather be in if I want to get from one side of it to another? Just imagine those roads. For this guy, we've got an electrical device with a constant resistance, draws 0.75 amps when connected to a 4.8 volt source, and we want to know what would happen if we up it to a 6 volt source. Now, this whole constant resistance thing is probably key. So easiest way to do this would probably be like just solve for the resistance. And so we can just start in the beginning where we know the voltage and the current, and we can find the resistance. So we could just say, hey, resistance is V divided by I. So we could say it's 4.8 divided by 0.75, which I think that would be sort of like times 4 divided by 3. So I think that would be 6.4 as the resistance. And then later on, the current would be, when we raise it to 6, our current would be I equals V over R. So we're taking our R hasn't changed when we up the voltage. So now it's 6 volts. We're dividing by 6.4. That looks like 0.94 to me. And then power is just equal to V times I. A bunch of other things too, but that's the easiest. And so if it's 6 volts at 0.94 amps, it's going to be a little bit less than 6, or let's say 5.6. So pretty sure that's the answer. Next guy, we got this delightful fellow. So we want to find resistance R2 here. We know R2 and R3 are identical, so these are exactly the same. So yeah, probably be handy to find the total current. So that's what I'm going to do. I'm going to say, hey, power equals I squared R. Because current through this 10 ohm is going to be the total current, because there's no way around this resistor. All electrons have to pass through it. So I'm going to rearrange this. So I equals the square root of P over R, which is equal to 0.4 divided by 10 square rooted, which is equal to square root of 0.04, which is 0.2 amps. So now that we've got the current, we've got total current, we can find total resistance. So our total resistance is equal to our total voltage divided by our total current. Our total voltage is 12. Our total current is 0.2 because all current has to pass through this guy. No way around it. This is effectively like multiplying by 5, so it's 60. 60 ohms is our total resistance. Now, if I subtract off 25 for these resistors that we know, that means this has to be the rest. So 60 minus 15 minus 10 gives us 35. So this parallel section is 35 ohms. But remember, if you've got two resistors in parallel, the net resistance is half what it would be. Like if you got three identical resistors, the net resistance is a third of the resistance of one of them. So if this is half the resistance of one of them, then R2 must be 70. So I'll write that out more. So here's your formula if you've got a bunch of identical resistors. If you want to find the parallel resistance of the whole section, that's equal to the resistance of one of them divided by how many you got in parallel. So in this case, our total resistance of the section is 35 ohms, and that's equal to the resistance of 1 divided by 2, because there's two of them in parallel. So if we multiply this up, we've got our 70 ohms, and so R2 is 70. Next guy, which the following graphs illustrates Ohm's law. You know how, like, if resistance is constant, which it tends to be, the V equals I times R. So if R is constant, if I double I, I'm going to double V. So whatever I do to I do to V if R is staying constant. So that would give me a nice straight graph where R is the slope. Nice constant slope because R is not changing. All right, next guy, we got this nice little circuit here. And we want to find the terminal voltage of the battery. So we'll just find the current by treating this as the real battery, and this is just one of the resistors. Two 6 ohm resistors in parallel acts like 3 ohms. Resistance of 1 divided by how many you got. They're identical. Which gives us a total resistance of 0.7 plus 2 plus 3, which is equal to 5.7. So our total current equals our V total divided by R total, which is 8 divided by 5.7. So our total current, 8 divided by 5.7, gives us 1.4, nicely. So we got 1.4 amps going through this circuit, and a couple ways we could do it. We could just do 1.4 times 5, because basically we want to find the difference in voltage between this point and this point. But the difference in voltage between this point and this point is the same as the difference in voltage between this point and this point. So we can just find the drop across these two, because everywhere connected by wires is at the same voltage level. So if I just did 5 times times 1.4, that would give me the terminal voltage, and that would be times 7 volts. Alternatively, I could use the standard formula. My terminal voltage is equal to my theoretical max voltage minus how much voltage I've lost across the internal resistance. So in this case, it would be 8 minus 1.4 times 0.7. Turns out 1.4 times 0.7 is basically 1. So again, I get 7 volts. So either way you cut it. Just double checking I'm not wrong, but I'm not. All right, we got this sucker. Now remember, everywhere connected by wires is at the same voltage level. So this switch here, assuming a certain voltage right here, has no effect on the voltage drop across X, and so it has no effect on the current through X. So it's got to be one of the sames. So it's got to be A, B, C, or one of those. Now, let's think what will happen if we basically take this guy out of action. If we take this guy out of action, suddenly we have reduced the, we've increased the total resistance of this section, so the total current has gone down, passing through Z. So Z will be dimmer. So we already know the answer is this guy. It's got to be dimmer because we've increased the resistance of this section, so it's going to have less current flowing through it, and all the current has to pass through Z, so it'll get dimmer. However, that current used to split evenly between Y and this guy, and now it has to go through Y, so Y is going to actually get brighter. You could also look at it as, hey, now this section is a bigger percent of the total resistance of this path, and so it'll have a bigger share of the voltage drop. So bigger voltage drop, bigger power, bigger current, bigger brightness for Y. All right, let's do this sucker. What is the power dissipated in this 8 ohm resistor in this circuit below? Seems like a good one where we got to find the net resistance and use it to find the total resistance and use it to find the current. That is probably going to happen. So first we need the resistance of the parallel section, and that's equal to R1 times R2 over R1 plus R2. Or you could use the 1 over R1 plus 1 over R2 business equals 1 over R total. Anyway, 12 times 8 is 96. 96. So we got 96, and 12 plus 8 is 18. They're both divisible by 6. This is 16. This is 3, so it's 16 over 3, which is equal to 5.3 repeater. So we got 5.3 repeater as the resistance of that section. Our total resistance is equal to 5.3 plus 10 plus 12, which gives us 27.3 repeater. Our current will equal our total voltage divided by our total resistance, or resistance, not current. And that's going to equal 80 divided by 27.3. Just a hair under 3, 2.93. 2.93 amps. Now, once we've got that, we can find the voltage drop of this parallel section. Though, if you wanted to be super fancy, you could be like, hey, this is like 3/5 of the total resistance, and this is 2/5 of the total resistance. So they kind of flip. We'll have 2/5 of the current going through this guy and 3/5 going through that, but that's probably more complicated than we need. Since we can easily find the voltage drop across the parallel section by just doing I times R for the parallel section. And that would just be 2.93 because all electrons pass through the parallel section in some way. And the resistance of that is 27 repeater. So times 27.33. Oh, sorry, 5.3 is just the parallel section. 27.3 is the whole thing, so it's getting 80, which is not very useful. So we do 2.93 times 5.333, and we get 15.6. So it's 15.6 volts from here to here, and if we just do 15.6 divided by 8, we'll get the amount of current that takes this bottom path, which should be 3/5 of the total, if you want to check that out. All right, so we will just say, hey, the current through R4 is equal to voltage across it, which is 15.6, divided by the resistance of it, which is 8. And we got 1.95 amps. That's how you do that, sucker. We've got light energy emitted by a bulb versus time. We want to find the power output of the bulb. Power is just change in energy per time, which also in this case, like, you know, anytime you got a formula like this, like if this divided by this is something, then the slope is that thing. That's this case. Because this is basically just rise or run. So if we do this, I'd say it goes roughly like, we got, say, +5.
My lone student that showed up to class today.
Cool.
How you doing?
Doing good.
Found a quiet spot to work, eh?
Yeah, I'm just recording a video.
Oh, sorry, shoot.
No worries. All right, so you got 7.6 watts out there. Now that's the output of the bulb. So if we want to find the input of the bulb, remember efficiency is equal to kind of like output divided by input. So if we want to find input, we can rearrange this. So input equals output divided by efficiency, which in this case is 7.6 divided by 0.2, which is the same as that, times 5. So we got 35 plus 3, so this should be 38 watts. So 38 watts input, we're only getting 7.6 out. This is definitely an older style bulb. And I think that's where I'll stop for now. Hopefully this helped. Thanks for listening.